I'm Jake O'Neill, creator of Animagraphs, and this is how the Grumman F-14 Tomcat works. Its design phase began in the 1960s, and it was officially deployed in 1974, in the midst of the Cold War. It's a Navy airplane designed to escort and protect ships and fleets. The F-14 is a relatively large craft to house a ton of advanced gear for long-range capabilities, but also excellent close-range engagements as well. The Navy learned through earlier failed programs that patrol-type craft like this would need both long and short-range skills. Excelling at both is what gives the F-14 its incredible staying power. The iconic variable sweep wings can shift from 20 degrees at their widest angle to 68 degrees sharp rearward rake, forming a perfect delta or triangle shape ideal for supersonic speeds. The F-14 can loiter, that is to say, fly slowly and methodically while continuously patrolling and monitoring a route, using its huge, heavy, advanced nose radar to search, track, and monitor many targets. With two cockpits, the pilot at the front for flying and immediate weapons duties, and the RIO, or Radar Intercept Officer, at the back to manage a dizzying array of high-tech gear. To counter a long-range threat, the wings sweep back as the plane bursts into a supersonic sprint, quickly closing the attack range gap before Soviet craft can launch anti-ship cruise missiles. At close, dogfight-type ranges, the powerful engines, variable wings, and flight control surfaces allow for fighting maneuvers, tight turns, high G-force pulls, and so on. A massive rotary cannon fires 20mm bullets through a nose opening. With Sidewinder missiles designed for close-range engagements. We'll keep these design goals and scenarios in mind as we examine the craft in detail. Let's jump right in, starting with the engines, and see what gives this hot rod her get up and go. I've chosen to feature components for the F-14B model, including these updated engines, which actually entered service toward the late 1980s, but were a major improvement over the original power plant. These are General Electric F-110 model jet engines. For a rough equivalent that normal folks like you and me can fathom, taken together at Mach speeds, the engines produce a staggering 50 to 80,000 horsepower. Let's zoom in on one side. Air arrives at the engine through special inlet ducts, which we'll see shortly. It's pulled in through a 3-stage powered fan at the front. Stage meaning a spinning ring of fan blades with stationary stator vanes in between, so air is forced backwards into the engine, building some pressure. This front fan assembly can be thought of as a really efficient ducted propeller. After the fan, some air splits to surround and cool the engine, and also provide fuel at the back for the afterburner. This is called bypass air, which makes some sense if, again, you see those front fans as a sort of propeller. The rest of the air enters the jet engine core. Where the fan is a low-pressure compressor, this is the high-pressure compression section. You can see how the air is forced through 9 compressor stages with their own spinning blades and stator combos into an increasingly narrow chamber. Compressing air like this is like forcing a powerful spring into a tiny box for explosive results once ignited. The compressed air blasts into the combustor section through a ring of small ports. Each port has a fuel injector and slanted vanes to swirl the air and fuel for optimal mixing. For starting the engine, there are 2 igniter plugs at the top and bottom that make a small electrical spark to light things up. Once burning, the reaction sustains itself as long as fuel and air keep passing through. This now super-powered ignited jet stream blasts through the turbine section, pushing against and spinning the turbines. These turbine wheels are what drive the entire engine, through internal shafts and gearing to transmit all that turbine power to forward fan and compressor stages. The violent jet stream, under normal power, enters the afterburner pipe where it mixes again with bypass air. The whole system here is still under high pressure compared to outside air, and the exhaust at the back is designed to accelerate this jet stream, just like a nozzle on a garden hose. The adjustable exhaust nozzle is a visually mesmerizing device, but simple enough once you see how it works. 4 actuators with bracing are attached to a stationary ring. With slots for a moving rod to pass through this ring. The actuators attach to and move another interior ring, which is where all the action happens. If I fade everything down to just one single set of plates, it's easier to take in. The first hinged plate has a curved ramp with a lip and slot to accept a set of wheels attached to that ring. The plate drops as the slotted wheel pushes against the curved track. Or raises in the other direction. The plates have multiple hinges and moving parts to maintain adjustment under intense workloads. A single exterior exhaust pedal covers the interior plate set, with its own fixed hinge point. And special sliding brackets at the tip that allow pedals to overlap as the opening narrows. Watching the whole thing operate is so cool. The design becomes intricate because it must not only withstand intense heat and pressure, but also the exhaust opening must be adjustable. At non-afterburner speeds, we can choke down the opening for optimal spray out the back. At full afterburner, the exhaust opens wide to release the entire jet blast. While we are building pressure inside the engine for better thrust out the back, excess pressure means damaging internal parts, or stalling out compressor stages and losing engine power as excess air blocks proper flow. So the whole thing is a finely balanced reaction, and the computer-controlled exhaust opening constantly changes to keep everything in its pre-designed sweet spot. Now let's back up a little and see what the afterburner does. Even though we get combustion in the combustor, jet engine turbine parts still can't withstand the heat of fully burning all oxygen out of the mixture. So, incredibly, there's still 70 to 80% burnable oxygen left in the ignited stream once it reaches the afterburner. And if we want to, we can add more fuel and reignite things to keep making more thrust. The trade-off is that it's not fuel efficient. Where the F-14 could fly for 3 hours or so under normal turbofan jet power, full sustained afterburner would empty the fuel tanks in 15 to 20 minutes. A ring of fuel spray bars sits about midway between core and bypass air. There's a flame holder ring in the flow path to give the air and fuel a place for thorough mixing, and protect the resulting flame from the rushing flow. A flame torch near the bottom of the engine ignites the ring. As afterburner power demand increases, core fuel spray bars become active, and a second flame holder ring ignites. At full power, the fan spray bars come on, and the final flame holder ring joins the flow with a massive supply of fresh, cooled, unburned engine bypass air for a ton of added thrust. Now you know how a fighter jet engine works in its entirety, because though things do change from model to model, this is a great basic primer. Let's head forward and see the specialized air inlets that help these engines breathe. There are 2 square ducts placed away from the center body or fuselage to capture cleaner airflows. The square shape, interestingly, relates directly to supersonic or Mach capability. Supersonic meaning past the speed of sound. Sound is a literal, physical thing that happens when air molecules bump into each other, eventually reaching and physically moving your eardrum. The speed of those vibrations or waves through air is the speed of sound. If you go faster than that, air molecules can't get out of the way quick enough and will tend to bunch up around surfaces that stick out or force air to change direction. The congested formations are called shock waves. At normal cruise speeds, the air enters the inlet duct, as you'd expect, flowing back to the engine. But as we approach the sound barrier, shock waves start to form. Inside of the engine, supersonic air will create unmanageable, chaotic shock waves around all these intricate moving parts. Our engine, simply put, cannot use supersonic air. So, we use a system of inlet ramps to tune airflow as it enters. Approaching the speed of sound at about Mach 0.7, a sharp, fixed external ramp in the F-14's bodywork gives the forming shock wave a defined attach point. The ramps start to move, forcing the air to change direction and generating a controlled shock wave that intentionally lands just outside the inlet lip. With slower subsonic air behind it, protecting the inlet from supersonic flow. There's a third ramp and port at the back of the chain to divert and bleed off any excess air to keep pressure and flow levels balanced. As we meet and exceed the speed of sound, passing Mach 1, the F-14's computerized system moves ramps farther. Using 2 ramps creates multiple waves that work together for a more controlled and predictable slowing of supersonic air. The ramp angles are programmed to intentionally place their shock waves just below the titanium inlet lip. Now it's easier to see why the inlet is angled backward and shaped as it is. It's all about managing supersonic flows. The squared shape is just to make these ramps mechanically easier to implement as simple swinging doors or gates, instead of trying to tune shock waves through a round opening, as some other supersonic craft do. The slowed down air gains a lot of pressure, so we're not actually losing too much energy. And while internal moving parts can't handle supersonic air, the engine actually prefers higher pressure for more powerful thrust spray out the back, as we just saw. We're ramming fast-moving air into an enclosed container, slowing and pressurizing it, igniting it, and then converting all that resulting pressure back into acceleration as the pent-up mixture blasts violently out the back through the exhaust nozzle. If we bring back the airplane exterior with all this fresh on our minds, it's also easier to see how wing sweep factors in. As we transition into supersonic speeds, a massive shock wave forms at the nose. Our wings gradually tuck back to their max 68-degree sweep as the main shockwave angle gets more severe with increasing Mach speeds, and the plane sort of rides inside of its own shockwave pocket. Otherwise, the sheer pressure at the sound barrier as air builds up would press against the unswept wing's leading edge, making the speed of sound difficult to surpass. While we're noticing the wings, let's transition a bit and see how the sweep mechanism works, along with other flight control surfaces. Built into the main fuselage, there are aluminum panels that form the wing root. Attached to this stationary structure, there's a synthetic rubber gasket to seal the wing as it sweeps. This combined area is called the wing glove. Underneath these panels, we see the wing sweep actuator, which is a huge hydraulically controlled screw instead of a standard smooth hydraulic rod you might expect. The moving wing structure attaches to the underlying aircraft frame here with a large fortified joint and bearing set. As part of the sweep system, there are inflatable rubber bags behind the wings that change inflation levels based on wing angle for a continuous aerodynamic seal throughout the sweep range. The wing itself has various moving flight control groups. Some of these parts are pretty common across aircraft designs. The leading edge slats ride on brackets with geared internal tracks. These work with flaps at the back that have their own actuators. At takeoff or landing, extending slats and flaps dramatically changes wing shape for max lift at slower speeds. An eyebrow door along the flap keeps the wing surface uniform with flaps up. But recedes into the flap face as flaps extend to create an ideal aerodynamic shape here. An accompanying cove door covers the interior wing structure. At the top of the wing, there's a row of spoilers that do various things. They can extend independently for roll maneuvers while wings are unswept. Working together, they can act like speed brakes during flight, or to dump lift and force the plane to the ground when landing. Moving to the tail, we see the large horizontal stabilizers, or slabs. At subsonic speeds, they work to pitch the plane front to back. As wings advance their sweep, they take on more duties, where at full sweep, these stabilizers also fully control roll along with pitch. There are two tail fins here to catch cleaner air around the body's sides for greater control versus a single vertical stabilizer. Cramming two huge engines into this relatively small package means a wider body overall. Movable rudders in each fin serve as yaw control, or rotation about the vertical axis. Between the fins, both above and below the body, we see the dedicated speed brake. Which extends to dramatically slow the plane down without requiring other adjustments. For example, if a pilot wants to quickly drop in behind another craft without altering a bunch of other settings or spooling engines down. Many of the hydraulic actuators that control these systems are servo actuators, where pilot input is augmented or translated by the unit, since surfaces would be too difficult to manage by mechanical means alone. Feel isn't direct in such a setup, so the system uses various techniques to give the pilot accurate feedback when flying. I could only find drawings or diagrams of the F-14's control chain, so while it's simplified and flattened, all the parts are here. This is the stick front to back, or longitudinal control chain to the stabilizers. There's a damper at the front, which is a magnetic device that can absorb sudden or jarring stick inputs to keep things under control during hard maneuvers. There are bob weight units at the front. and mid part of the system to add weight feel to the stick when pulling harder G-forces. A cam and roller package adds artificial resistance as the stick travels deeper into its range, with a small wheel that travels along an inclined track. There are tie-ins for various computer controls, trim, and the input from the lateral or stick left to right chain, with a mixer to blend all these inputs. The pilot might want to roll the plane, but that can enlist an orchestration of various surfaces at once that the system will seamlessly blend together. By the way, the lateral or stick left to right chain is an entire separate set of parts that looks every bit as complex as this diagram. And this is just for the stabilizers. Flying is one thing, but landing is another for a craft like the F-14, which is designed to operate from an aircraft carrier. Here at the rear, below the flat body feature called the beaver tail, you can see the arresting hook. This is the hook that catches on a wire at the aircraft carrier deck surface to stop the plane. It's quite large and ties into the frame itself, since it must absorb much of the aircraft's weight and landing force. The unloaded F-14 weighs about 43,000 pounds, with a max specified landing weight of 51,800 pounds. The hook has a rubber bumper against the body, a release mechanism, and a damper called a dash pot at the hinge side for smooth lowering when unlatched. Another actuator brings the hook back up again. The rear landing gear folds neatly up underneath the body at the sides. With multiple doors and a rotating action at the end, so wheels sit flat in the wheel well. The front landing gear extends out from the body with doors of its own. It has a launch bar at the front that connects with a shuttle on the aircraft carrier deck surface for the takeoff catapult sequence. The pilot controls a function which lowers the front landing gear shock strut by 14 inches, essentially kneeling the whole craft at a downward angle. This keeps the plane from wanting to lift off the deck prematurely, and also preloads the front shock, so that when released, the nose gets a desirable upward bounce or boost at takeoff. At the other side, there's a connection for a holdback bar that's designed to break free once engines reach a certain thrust force, releasing the plane and allowing the shuttle to launch it forward. A wheel at the launch bar tip rolls along an interior surface to fold it flat when retracting the front landing gear. The landing gear is beefed up to handle hard carrier landings. It's all attached to the plane's internal structure or airframe, which is made of aluminum panels, titanium, steel, and other composites. Back toward the front, let's see how crew enters the plane. There's a flush-mounted latch that pushes in to release a triple-section folding ladder. Two concealed steps can be opened from here for entering the pilot or reconnaissance officers' cabins respectively. We'll head up into the cockpit and see what the pilot sees. There's just something captivating about a physical interface with this much detail. All the different switches and knobs with defined and deeply studied shapes and functions. So many systems all converging in one space that a skilled pilot must know and understand. At sight level, we see the heads-up display, which is projected onto the front glass through a small projector head at the top of the dashboard. It can display various things. I'm showing the angle of attack bracket, which indicates the wing angle relative to oncoming air. Exceeding certain angles at various speeds could mean a loss of lift, for example. Along with vertical speed, meaning how fast the plane is dropping or rising in air. And the velocity vector, which tracks the plane's trajectory relative to the horizon regardless of the plane's angle or attitude. Altitude. And the weapons reticle. To the left, there are warning lights related to landing gear and landing aids for the demanding aircraft carrier landing sequence. At the right side, the warning lights indicate different types of enemy radar lock-ons. At the top of both sides, there are left and right engine compressor stall warning lights. The top dash panel here relates to weapons systems, both the gun and any missiles, bombs, and so on. There's a physical angle of attack indicator to the left, and a wing sweep gauge to the right. Down the center of the dash, there's a screen that basically repeats what the windshield projection is showing. The screen below that can track a programmed heading or coordinates, showing deviation from the path, distance, and more for flying to specific points on a map. To the left and right, there are some fairly standard aviation gauges. An airspeed gauge that also measures Mach speeds, a physical vertical speed indicator, and two different types of altitude meters or altimeters. The radar altimeter bounces radio waves off the ground to measure altitude and is great for low altitude flying. The other altimeter uses air pressure to calculate altitude, so it's a little better for high altitude flying. Below that, there's a cluster of gauges for engine and hydraulic related systems. And vertical gauges for engine RPMs, exhaust gas temperature, and fuel flow. Over to the right side, we see the standby attitude indicator, which shows how the plane is oriented in space, repeating data that's already likely on screen. There are two radio frequency readouts because the F-14 uses multiple signals to transmit all kinds of communication and data to control just about everything on board. There's an analog heading tracker below that. and a radar warning display to track hostile radar signals from many sources, like other aircraft, weapons, and so on. At the pilot's control stick, we see an array of ergonomic switches. At the center, there's the pitch and roll trim hat, with up-down for pitch and right-left for roll. Trim is a standard aviation feature that adds permanent adjustment to flight control surfaces, reducing pilot workload in steering the plane. The small red button is the bomb release. And the hat selector switches between various weapons stations or the onboard gun. The thumb wheel below controls modes for the slats and flaps for combat maneuvering versus landing. A nearby button handles various items, like dispensing countermeasures. The trigger at the front fires the selected weapon. A button below toggles nose wheel steering while on the ground, or autopilot modes if airborne. And a large paddle beneath the stick disengages autopilot. Down the left side from the dash, there are indicators for flight control surfaces, landing gear controls, and fuel system switches. To the pilot's left or port side, we see the main throttles. The military power range is normal engine operation, with a detent that the pilot must push past to engage Afterburner up to max power. While wing sweep angle is generally automatically controlled by complex onboard systems and computers, it can be manually set with the hat switch here. There's a speed brake toggle switch, and another switch for radio communications controls. An emergency wing sweep lever down below engages a redundant emergency hydraulic system for wing sweep. Panels continuing aft here include more engine controls, rudder trim, and the AFCS and autopilot controls, where AFCS is artificial stabilization to improve aircraft handling, and autopilot controls computer-guided flight towards exterior headings. A main radio control panel sits nearby. And the Tactical Air Navigation Panel, or TACAN, for radio tracking of ground or shipborne beacons for navigation. Over to the pilot's right or starboard side, there are controls for the arresting hook, a gun rounds counter, and below that, a panel that manages both displays and their various functions. Farther to the side, there are spoiler emergency systems toggles, and a panel for caution or warning lights. Here at the cockpit center, we see the pilot and ejection seat. The seat has some fairly standard functions. The pull handles at the top bring down a face curtain to hold the pilot's head against the seat to avoid flailing injuries. And there are leg garter braces to pull in and secure the pilot's legs for the same reason, since ejection is a forceful, rocket-propelled process. The lower ejection handle can be used if needed, for example, if high G-forces pin the pilot's arms down, making them hard to lift. The pilot wears an oxygen mask. And a special G-suit that straps snugly on over the flight jumpsuit and is connected to onboard air. During high G maneuvers, the suit inflates to squeeze extremities and help keep blood flow towards the core and head instead of pulling away from the body's center. Heading aft, we see the RIO, or Radar Intercept Officer's cockpit, which I've graphically simplified for the purposes of this video. Since the F-14 is a reconnaissance vessel, the RIO controls an advanced array of high-tech gear to manage all tracking systems, warfare planning, communications, and weapons deployment. Where the pilot flies the plane and manages immediate engagement, the RIO keeps track of overall mission goals. Behind the combined cockpits and to the sides, there are compartments for onboard tech gear. All the space we haven't seen yet is basically filled with a system of fuel tanks. The F-14 can carry about 16,000 pounds of fuel, which roughly equates to around 2,400 gallons. A probe extends from behind the starboard panels for air-to-air refueling. Our bird can carry an array of weapons, gear, extra fuel tanks, or special reconnaissance modules on its underside mounting pods. I'm showing a general loadout here, with 2 larger Phoenix guided missiles for longer range targets, and 4 smaller Sparrow guided missiles for close range encounters. Tucked underneath the pilot's cockpit, we see the M61 Vulcan rotary cannon. Which fires 20mm rounds at 4,000 to 6,000 rounds a minute, though it only holds a total of 676 rounds with a large ammunition drum at the back. At high fire rate settings, it would empty in about 7 seconds, though it's most often used in short bursts at a time. As for equipment, countermeasures like chaff and flares are deployed from a compartment in the rear tail area. Various probes cover the sides of the craft for computer-driven gauges and also onboard analog equivalents for airspeed, air pressure, angle of attack, and more. The positionable nose radar dish takes up the front nose area. The radar system can track up to 24 targets simultaneously, with a 195-mile radius. It can launch and guide all 6 onboard missiles at once, while still monitoring other targets. For comparison, other fighter craft at the time had radar that could only see 30 to 50 miles and needed to lock on to just one target to engage. The chin pod houses cameras and more radar gear. It's rare for anything to be good at so many disparate tasks. and handle them or even excel at all of them. Oftentimes that might lead to an over-designed thing that sort of fails at everything. So when something comes along that meets and surpasses such lofty design goals so that it's useful for decades at a time, that's what I'm interested in. It's clear that entire buildings of incredibly skilled people poured their knowledge and talents into the F-14 for a legendary result.